Welcome to this explainer. Today we're exploring a massive, practically invisible challenge that's happening all around us, literally every single day. We're looking at how advanced machine learning is stepping up to solve one of the world's absolute biggest energy efficiency problems. Seriously, if you've ever wondered how modern cities manage to keep the lights on without just wasting enormous amounts of energy, well, you are in exactly the right place.
Okay, let's dive into this. Just think about it for a second. Every time you flip a light switch, crank up your AC, or plug in your phone, the power is just there, right? But here's the catch. Electricity isn't easily stored on a massive citywide scale. It actually has to be generated in real time to match exactly what we're consuming at any given moment. So how on earth does the power grid know exactly how much electricity millions of people are going to need tomorrow?
Well, the answer is short-term load forecasting, or STLF for short. Basically, this is the science of predicting electricity demand hours or even days in advance. By using machine learning to boost STLF accuracy, grid operators can perfectly balance the power supply with our demand. And honestly, perfectly matching that supply is the absolute cornerstone of keeping the grid stable, stopping energy waste in its tracks, and drastically reducing carbon emissions so we can build truly sustainable cities.
Because getting this forecast wrong, it has massive, real-world consequences. If an operator overestimates how much power we need, they end up turning on extra power plants for absolutely no reason. They're just burning excess fuel, wasting energy, and driving up operational costs. But what if they underestimate the demand? Well, that's when we get hit with severe energy shortages, dangerous voltage drops, and those community blackouts nobody wants. It's this incredibly high-stakes balancing act, where accuracy isn't just about data, it's about keeping society running reliably.
And this brilliantly illustrates the solution from a really groundbreaking new research paper. So instead of just relying on one single algorithm to predict our energy future, the researchers proposed a brand new weighted ensemble model framework. Basically, this approach takes three distinct, totally powerful machine learning models and fuses them together into a single, highly robust superpredictor.
You can really think of this as a dream team of machine learning experts. The core of this new ensemble is something called the regularized greedy forest, or RGF algorithm, and it joins forces with two absolute heavyweights in the gradient boosting world, XGBoost and LightGBM. Since each of these models processes complex variables, stuff like weather data and calendar events, in slightly different ways, they each bring completely unique strengths to the table.
XGBoost calculates sequentially. It looks at the errors or the residuals of its previous decision trees to build the very next one. RGF steps back and optimizes the weights for the entire forest structure all at once, right after it's fixed.
Let's move to and see how this builds in a real-world application. The researchers actually took this RGB-based ensemble model right out of the lab and tested it using a massive dataset of actual daily operational utility data. They tasked the AI with conducting 24-hour day-ahead load forecasting, feeding it real-world variables, things like previous energy loads, the day of the week, holidays, temperature, and even heat indexes. And guys, the results were just stunning. 1.60%. That is the mean absolute percentage error, or MAPE, achieved by this proposed ensemble model in real-world day-ahead forecasting. Think about that. To predict an entire city's energy demand 24 hours into the future, hour by hour, and only be off by an average of 1.60%, that is a monumental technical achievement. To put that into perspective, an error rate that incredibly tight translates directly to perfect supply matching, which means unparalleled grid stability. Because the model predicted the demand so well, operators wouldn't waste fuel turning on unnecessary generators. And on the flip side, they wouldn't risk blackouts either. In the actual experiments, this RGF, XGBoost, and LightGBM ensemble actively outperformed standard deep learning models, proving it's incredibly practical for real-world sustainability and huge emissions reduction impacts.
Now, what's really interesting about this slide is that if you want to dive deeper into the equations and see exactly how this ensemble outperformed standard deep learning models for yourself, you can read it directly from the source. I highly recommend checking out the original open access research article in IEEE Access. It's titled Short-Term Load Forecasting Using Regularized Greedy Forest-Based Ensemble Model, and it's honestly a fascinating read for further exploration.
Thanks so much for joining this explainer, and stay curious.